Okay, welcome back everybody to E340 542. Today we're going to be talking about expansions of the SIR model in two directions. We're going to talk about adding stages to the SIR model. We're going to talk about stochastic simulations, which are quite easy to do in antimony. And we'll also talk a little bit about the idea of fixed points and steady states. I need to remind you the class is live streamed on YouTube and is recorded. So today we're going to start out by going over actually a more complicated model, which was the one in the homework. And I'm going to wing that a little bit and work on that with you. So I'm hoping that you can all use what you were able to achieve in the homework and we can do this together. And then we'll talk about stochasticity, how to define events, which are simple programming concept in antimony, maybe a little bit about function definitions in antimony, fixed points, and then some of these other model structures. Once you start with the basic SIR model, there are more or less limitless number of variations. Really, the names are sometimes descriptive, sometimes not so descriptive. There are a couple of basic features that we'll get, and we've already explored this in the homework a little bit. So just coming back to what we did last time and looking at the homework, one of the things that we did was look at the active case numbers early in the epidemic. One could also look at the new waves of the epidemic. Actually, it'd be interesting to compare the numbers that you get from the first wave of the epidemic with the numbers you get from subsequent waves. We looked at the active cases, and as I reminded you some time ago, the active cases are a little bit artificial because while people in the hospital are discharged and therefore you know they've ceased being an active case, if the cases are reported by people in the general community, they don't report when they stop being sick, and therefore they actually assume the duration of the active cases. And so the trailing number of active cases is a little bit artificial. You'd like to have that number more accurately. And so the way we looked at that curve, we see a rapid increase of saturation and then a slightly slower decrease of case numbers. And we first estimated the recovery rate mu, and we did that by hand using the application that we had in NanoHub, where we looked at the tail end, put it on a semi-log plot because we expect it to be exponential. We pick two times that are convenient where there's a roughly linear decrease of the value. We look at the change, fold change in the value, take the logarithm of that, and then the time difference, and that gives us a rough estimate of mu, the recovery rate. We then look at the leading edge of the infection, and we again put that on a semi-log scale. We look at the fold change, take the logarithm, divide by the time difference, and that gives us a rough estimate of that beta parameter and gamma over S naught times S. And the one thing that we have to watch out for is in principle, mu enters into that. And so we've got that there. In practice, probably n gamma is bigger than mu. And so it doesn't make a huge difference. And that allows us then to calculate R naught and S naught. And I think that most people were able to come up with their own values of R naught and put them into the table that we had. I left the values from last year, from the students in the class last year, just so you could see whether or not that your estimates agreed. Did anybody have any issues? I know some people had trouble loading the New Zealand data set, but some people seem to be able to get it to work. Are there any comments, questions about that exercise that we want to go over now?
I wasn't able to get into the spreadsheet. I was able to get into the Google Doc, but I wasn't given access or something.
So when you try to go in, it should ask you if you want access. And if you ask for access, it should send me an email and I can then authorize it. There's always a problem with Google, which is that if you share it to a non-Gmail account, you have to do double authorization. And I'm sorry if I missed the request. If you go into that spreadsheet and ask for authorization again, I can certainly go back and add it, or if you email it to me, I could put it in for you either way. Did other people have trouble? I know Ryan, I think, was able to put in some numbers there. There's always a possibility of with these Google products that if you don't have a Gmail account, they can be a little bit of a pain. So I apologize about that. What did people get? What did you get as your estimates for R naught for those data sets? People could just type it in the chat if they like. If everybody types in the chat your R naught estimate, we can take a look. For Italy, say. Or is it too long ago you don't remember? Anybody? Nobody willing to volunteer? Somebody should volunteer value for R naught. Okay, thank you, Delaney. Italy, R naught 5.27. Anybody else? Benjamin, did you get a value for any of the R naughts? Or Colin?
For New Zealand, I got 4.07.
Okay, 4.07 for New Zealand. Colin, were you able, did you get any of them? Drew? Okay. Well, so we have two values of 4.07 and a 5.2. That seems about right. R naught is not really a property of the virus by itself. It's a property of the virus plus the social situation. And so you don't expect to get the same number exactly, especially when you're doing an eyeball fit like this. But Spain, okay, Delaney says Spain was about 4. So New Zealand 4.5. Great. That's great. So I'd say that people would be comfortable with the base R naught before they started putting in a lot of social distancing and shutdown of about 4 to 5 for the alpha variant. So that makes a lot of sense. Okay. The next thing that we had talked about was the idea of herd immunity. And back now, 2 weeks ago, the homework that you handed in last week, and always I'm reviewing the homework problems late because you hand them in and then it takes me a few days to get them graded. And so I can't talk about them till the following week. But there was a very simple question which said, what is the herd immunity threshold for the epidemic? And that's 1 minus 1 over R naught. And so if R naught is about 5, 1 over R naught is about 0.2, which means you need about 80% of your population to be either immune through vaccination or prior infection. And so that's an important number. It's not a perfect estimate. The herd immunity threshold is never exact. Even if a disease is highly infectious and there's no immunity, not everybody gets it. Somehow there are isolated populations that don't get it, and so on. And so that lowers the herd immunity threshold a little bit. On the other hand, there also are always people who are not immune for one reason or another, or the immunity doesn't last forever, and that raises the herd immunity threshold a little bit. Which of those mechanisms dominates will be dependent on the virus and the population. But if we assume that the R naught for alpha is between 4 and 5, then 1 minus 1 over 4, 75%, 1 over 5 is 0.2, so 80%. So that means the herd immunity threshold for alpha variant was on between 75 and 80%, which already means that a lot of people have to get sick if you don't have a vaccine. If we look at the immunization rate in the United States of 60%, that means that something like 20% of the population has to get the disease before we reach herd immunity. And unfortunately, that will happen. The disease isn't going to go away without stronger social distancing measures. And therefore, it means that if we don't have higher vaccination rates, you're going to get it was not going to stop till 20% of the population has gotten it. So there are these tables that you can look up for how for the R naughts. And you can think a little bit in the homework, and we talked about this, about ways of reducing infection. We will run over that in the past. When this slide was made a year ago, they didn't really have a vaccine out yet. So clearly, vaccines are the best thing to do. It wasn't clear at the time either that how long the vaccines would last. Looks like the vaccines last about 6 months, 8 months, which is okay, but not fantastic. The good news, I guess, is that if you're triple vaccinated, your protection really does seem to be quite good. And there were this table that I pulled, which gave some typical R naught values for some different viruses. Again, you have to remember also bacterial infections. So it's infections rather than viruses. You have to remember again that these R naughts are socially determined. And we've had some good presentations in the IMAG working groups on those Thursday meetings about people talking about social factors that influence viral spread. But if you look at a disease like measles, it's extremely infectious. Whether it's 18, 15, or 20, hard to say, but it's big. And that means the threshold for herd immunity is 95% or higher. Influenza, they give a R naught of about 2. I think most people would actually say the R naught slightly higher for influenza than that. classic SIRS was between 3 and 4. Notice for malaria, they give a huge range of R naughts. That's because it's spread by mosquitoes. And so you're highly dependent on the number of mosquitoes and the particular species of mosquitoes around. So those are all pretty problematic. The other thing that we spent quite a bit of time on, and that's why we actually, our lecture quotation marks behind, I don't think we lost time at all. We just spent more time on things, was on optimization. And Josh gave 2 lectures on optimization. And it's something that really is a critical skill to learn. There are a bunch of concepts in optimization, some of which are relatively straightforward, some of which are not straightforward at all. We have the idea of an experimental data set. We have a model. That model has some set of parameters, and we'd like to adjust the model parameters so that the simulated data set and the experimental data set agree as closely as possible. And there are a whole series of points that are rather complicated in that statement. One of which is that there may be, you could have the wrong model structure so that there is no set of parameters that agree with the experimental data. Another thing is experimental data themselves could be noisy or incorrect in some way. A third thing is that the times at which experimental measurements were made may be uncertain. And so we typically think of uncertainty in the value of variable, but we also really have to consider uncertainty in the time at which the measurement was taken. And that can be a little harder to deal with computationally. Another thing is that when we say agree, we have to define a metric for the distance between the experimental data set or the target data set and the simulated data set. The classic metric is a root mean squared error, chi-squared, where we take the distance at each time point, which we've measured between the experimental data set and the computed data set. That could either be positive or negative, so we square it to make it always positive. We sum those squares, and then typically we take the square root of that. Sometimes we don't. And that's the classic metric for deviation. That works fine if all of the values that you're trying to compare are roughly of the same order of magnitude. However, if you have a situation in which sometimes the values are 10 to the 6th, and sometimes the values are 1, the order of magnitude of the deviation is typically proportional to the value. And so chi-squared measurements are primarily sensitive to deviations in large experimental values. And that may be fine. That may be what you care about. Maybe what you really care about is what's going on when you have a lot of people infected, not what happens in the background when there are few people infected. But sometimes you care about large values and small values equally. When that's the case, typically you take the logarithm of the values and then do chi-squared on top of that. And there are all sorts of complicated error functions that weight large and small values differently to try to account for the differences in what you're trying to do. So there is no perfect error function. The error function that you use fundamentally is going to depend on what you're trying to do, what's important to you in the problem. And so typically in numerical optimizers, you'll return a function, you'll have a function, you'll define a function yourself, and Josh showed you how to do this last week, that calculates the error between the calculated data set and the experimental data set. And you have some freedom then to decide what you define as the important error. Another thing that often happens is if you have a single data set, then that's a little more straightforward, but you might have 4 measurements. For example, for our SIR model, we have the number of uninfected individuals, S, the number of infected individuals at any given time, I, and the number of recovereds. Now, the sum of those 3 is the total population, so we don't need all 3 of them. But S and R could vary independently of each other, partially independently of each other. And so if we had experimental data on both the number of uninfected people and the number of recovereds, or the number of infecteds and recovereds, we might want to fit both of those into both of those. And then we have to decide how to combine the error from the fit of S with the error from the fit of I or R. And that typically is a linear combination with some weight factor. Ideally, you adjust the weight factor so that the contribution of the 2 errors is about the same. You don't know that in advance, though. And so there's another set of parameters, hyperparameters, if you're used to doing AI work, hyperparameters that define the structure of the error function and how you combine error functions for different time series. So the defining what agreement means is not always simple. And then what you want to do is you want to find the set of parameters that gives you the smallest error. And you find that there's a problem, which is that as a function of the parameters, very often there are local minima in the error function. And optimizers have a tendency to get stuck in those local minima. And so typically what you'll need to do when you're doing optimization is to start from a bunch of different initial conditions and hope that at least one of them converges to something like a global optimum. And you did run some examples of that last week. And I reassigned that homework problem that we had originally been from the week before to do some exploration of optimization. In your projects, I'll expect that you do more of that. And so it's important to try to begin to get familiar with the optimization. It's a big field, and one could spend a whole semester on optimization, but at least the basics are important. So one of the things that I want to talk about today is something that came up in the homework, which is not so complicated perhaps, but is a term you may or may not have run into, which is a fixed point or a steady state. And so in our systems of equations, typically we have rate laws. A rate law is an equation, an ordinary differential equation in time that has the form d by dt on the left-hand side equals some function of the values of the variables. And so in an SIR model, we'd have 3 rate equations, one for S, one for I, and one for R. And the rate of conversion from S to I or I to R will be a function in principle of S, I, and R. And so we'll have a functional form that looks like that. A set of variables values, S1, I1, R1, for example, is called a fixed point of these equations if for those values, the values of the variables don't change in time. So the time derivatives are 0. So if I write the rate law as a function of the variables, those functions, F1 for the first rate law, F2 for the second one, so on, have to all be 0. There are a number of different notations that are used commonly to denote fixed points or steady states. A star in the numerator is a pretty common way of denoting a fixed point. And Tellurium in principle will find steady states, but in practice, the steady state solver doesn't always work. And so we'll typically run simulations for a long time and make sure that they reach steady state rather than using the steady state solvers. but you may want to investigate the steady state solvers in Tellurium. If you look at the Tellurium cheat sheet, there's a get steady state function that is like the integrate function, the solve function, the integrate function that does, in principle, give you the solutions. And I have to say, I'm not exactly sure why it fails sometimes. My recollection is that a couple of years ago it worked more reliably, and I'm not sure what happened to it. So we've stopped using it so much, but it's there. So let's just think about a fixed point or a steady state now for our simple SIR model. Our SIR model was ds by dt is equal to minus beta times I times s. di by dt was beta times I times s minus mu times I. And dr by dt is equal to mu times I. And now we want to find a value of s, I, and r such that the right-hand side of each one of these is 0. And we can look at the first equation. The first equation is bilinear in I and s. And so the right-hand side is 0 if I is 0 or if s is 0. If we look at the right-handmost one, dr by dt equals mu times I. Mu times I is only 0 if I is 0. There are no other possibilities. And let's look at the middle one. The middle one is beta times I times s minus mu times I. We can distribute the I out. It's I times n gamma over s naught s minus mu. So that is 0 if I is 0, or if n gamma times s over s naught minus mu is 0. So that second one was equivalent actually to our herd immunity threshold as follows. So it's not really a very exciting problem. We have a limited amount of information that's useful. If I star is 0, then for any value of s, s stays constant and r stays constant. So s comma 0 comma r is a steady state. And if I is not 0, then we can't have a steady state for R. So that's about all we can do. If we are at the herd immunity threshold, S star over S naught is equal to mu over n gamma. That's the herd immunity threshold. Then that's going to give us a steady state for S, no matter what the others are. So what I wanted to do now was to try to do that homework problem a little bit together, see how it goes. If it doesn't go well, we can give up and try something else. But I would like to look at to do this together because I think it was a pretty important problem, mainly from the point of view of actually thinking about the epidemic. I know a lot of you got it. If you got it, let's help us each other do it. If you didn't get it, then this is an opportunity to go over it. Maybe I should actually poll people before I do anything. If everybody got it, then maybe we don't need to do it. But I'm going to use the regular poll, and if you were successful in solving both of the problems about the SIRS model and the model with the virus, click finished with exercise. And if you were unsuccessful in doing it, why don't you click need more time? And so we can just get an informal poll of how people did on that. So one person hasn't responded, so I need to wait till everybody responds. There we go. Okay, so 2 people got it, and 3 people weren't quite satisfied with their results. So why don't we do it together and see how far we can get? And I should say I did this homework problem. First, there was a typo in the homework problem, which I apologize for. And actually, the typo is here in the I cut and pasted the wrong version of the homework. I actually have the typo in the slide. So I appreciate your patience with that. But I did do it myself before I assigned the problem, and then but I haven't got it set up now. So why don't we think about this together for a minute? And let me just stop the screen share for a second and get, actually, I think it should be all right on this. Let me get the screen set up so that we can see things together. So I'd like everybody to launch Tellurium, whether it's on your desktop or on NanoHub. Okay, great. So thanks, Benjamin. If you can help us out, if there anything, then we can see if we all get the same answer or not. As I say, there's a typo here. Let me see if I can actually fix that. I don't think. Sometimes PowerPoint will let me edit PowerPoint while it's displaying, and sometimes not. In this case, it seems to not want to display. There is a typo here, which Delaney caught, which is that R goes to S. The rate should be R over tau, not S over tau. The rate at which recoverads become susceptible again has to depend on the number of recoverads, not on the number of susceptibles. And so that was a typo. So let's just look at this equation together and think about how to write it. And I'd like everybody to do this together. The first thing that we have is we are going to take S goes to I, which we have here. And let's call it I1 just because I think I is all right. We'll find out. Occasionally we'll run into reserved words in Tellurium. They're not obvious. And the rate is going to be beta times S times I. And that's the rate of infection. Okay. Does anybody want to give me the next equation from the and please follow along and do this. Let's do this together. What would the next rate law be from the arrow diagram that we have there? So it would be for I goes to R. There we go. Thank you. So I goes to R. Type it more in line, and we said that that was mu times I. That's the recovery, right? That's okay. And then we need to do the last one. There are only 3 equations. The one from R to S. Anybody? That's good. Well, I'm sure it's more interesting to watch a YouTube than it is to solve the SIR equation. No problem. So what would our rate be? Anybody for this? suggestion. There we go. R divided by tau. So this is the loss of immunity. All right. And we, instead of specifying beta, here I specified n gamma over mu. And so let us define the initial population S naught, and that was 10,000 I said to use. And we'll assume that 1% of the population is initially infected, so that would be I equals 0.1 times S naught. And actually S, our initial S, would be 1 minus that, so it would be S naught minus I. That'll give us our initial population of 10,000. And what else did we say? We said that R naught was equal to R naught. There wasn't really an input here. Go away. I'm not doing anything.
If it's 1% of the population, shouldn't it be I equals 0.01 times SO?
Thank you very much.
Yes, sir.
Thank you. Appreciate it. As I say, you can probably type this faster and do it faster than I can. I'm following along. And so what we needed here was we said R naught was equal to 4. And we said that tau was equal to about 6 months. So 6 times 30 is the duration of immunity. R naught is 4, so this is our initial infectivity. Replication, right? And then we have to figure out what mu is. And the key thing here is that mu is shorter than the actual time you're infected. Typically, the COVID infection lasts about 2 weeks, but you're really only infectious for about 4 days of that. Not because you're not infectious later on, but because you're so sick you're not spreading it. And so the typical assumption is that that mu value is about 1/4, or 1/4, which is the recovery rate. It's really the duration of infection. All right, and then we have to convert to get our n gamma. We need to get the invert this R naught equals n gamma over mu. So that would be R naught times mu. So we'd say beta is equal to R naught times mu. And then we have to remember that beta has the total population factored into it. And so we need to divide this beta by the total population, S naught. Because this really is S times the probability that any given individual is infected. That's not I, but it's I over S naught. I could have put that in there maybe instead. So that I think should be about right. Does that seem right to people? Let's see. Let's have a vote on. Whether they think that's right. And why don't you tell me if you got this typed in yourself? Okay, everybody got it. So let's see if it works. Oops, typo. Oh. Huh. Error. Says I failed to define T naught. Oh, that's not. There is no T. So it's the extra one. There we go. So that's what it looks like when I run it. And you'll notice that 10 days is not nearly long enough. And one of the things I asked you to do was think about how long things should be. When you add time, you also have to add points to your simulation. I have to begin with making the number of points in the simulation about 10 times the number of the time. It's not a bad one. I think, let's see, I think Antimony will pick that number automatically if we don't specify the number of points. Let's try it. Yeah, so it'll interpolate it itself if we don't tell it explicitly how many points to include. And did people get something that looked like that? How many people got something that looked like that? So here we see that the initial epidemic is over a period of about 20 days. And then the number of recovereds goes up to about 8,000 and then slowly goes down again. And let's see how long the epidemic really takes to peter out and increase the target time, the end time. And we see something that's interesting. We see that with the SIRS model, we get waves. There's some jaggies here, so I do have to specify how many points I'm going to use. We get waves. We get initially a small number of people are infected. We get a peak of infection. And then the infection seems to go away, right? The number of infected individuals goes down to nearly zero. But as time goes on, our number of recovereds who are resistant goes down. At some point, namely here, around 150 days, we're below our herd immunity threshold again, and we'll get a second peak of infection. And then here, another 150 days later, we get a third peak of infection. And you'll see that if we extend this out even more, oops, too many points, all right? You won't let me do that. What we see is that we get a decaying oscillation, and eventually we reach a steady state. And we'll notice that our steady state has some fraction of people who are recovered, 6,000 here. So 60%, 40% are susceptible. And it's a little hard to see what our value for I is. So why don't I actually print that value for I? I could do, let's see, let's edit. Let's add a cell. Let's see why it's not giving me a cell underneath. Insert cell below. So let's print the value of I. Sorry, m dot I is 129. And to know what that is, we have to divide by the total population, that's 0. So about 1% of the population is infected at any given time. Did people get something similar to that? Everybody got it? Okay. So we can also ask what's the maximum fraction of the population infected at any given time. To do that, we have to do a little bit more work because we actually have to find the maximum value in that column. And why don't we think about that a little bit together? Before we do that, let's look at the Delta variant. So the Delta variant has a much higher R naught. It has an R naught of about 10. So why don't we put in 10? We put in 10. Doesn't look that different here. Let's see what happens in terms of our fraction infected. Okay, I made a mistake. What did I do wrong? Let's see what I did wrong. R naught is 10. Tau is 6. Mu is 1/4. Oh, because I've got beta redefined. Nobody caught that. My mistake. Let's run this again and do it right. Okay. So we get beta now is 4. R naught is 4. Beta is R naught times mu divided by S naught. R naught times mu is 1 divided by S naught. And that gives us final number of percentage infected of 0.121%. And now let's try making R naught 10. And if I make R naught 10, I'm confused here, actually. What am I doing wrong? Somebody see what I'm doing wrong? Giuliano? Let me go for a shorter amount of time. It has changed the oscillations. The number of people infected early on is much higher. And the period of oscillation is faster. So the value of R naught does make a difference. So it's not that I'm not changing that, but the final, oh, I know why, because I didn't rerun it today. For R naught equals 4, I get the final value here. There's still some oscillation, about 1.5%. If I make it 10, let's see, it's about 0.2. So there's some change, not huge. The big difference is the peak, the size of the peak. So if we wanted to change, if we wanted to find out how to find the maximum number infected, what would be a good way to do that? Does anybody have a suggestion for how to find the maximum number infected at any given time? If somebody has some code that they think would do that, you could put it in the chat if you like, and we could see how to do it together. Yeah, that would be fine, Benjamin. So one way to do that, Benjamin says use the max function on the list of the numbers infected. So how would we get a list of the numbers infected? in our simulate function, we can tell it that we want to have just the number infected, which we called I. I have to put in quotation marks. Yeah, that would work too. Maybe we should, let's try Delaney's method better. That maybe is better. So we'll say what we want is max I equals max of S and then an iterator, and we want the second column. People think that's going to work? And I'll print it in here so I don't have to keep remembering to print max I. Does that seem right to people? Find out. So max I is 6,000. Let's divide through by the total to get the max percentage of the population infected. 67% of the population gets infected at once if we have a R naught of 10. If our R naught is 4, 40% is the maximum. Great. So that's a good thing to do. We could run, if we wanted to see the dependence on a parameter. Some people, I've been asking people to do parameter plots, and I've been not getting too many parameter plots in the homework. Is it confusing to try to figure out how to do a parameter plot? We had a few examples earlier in the class where we did it. Would it be useful to do that together, or do people want to try? Why don't people take 5 minutes and try to do the parameter plot now as a little exercise, a mini exercise. So let's take what we have here, which is max I, and let's plot max I. What's the easiest one? If we change R naught, the problem with changing R naught is that we actually have to change beta by hand. So we can do that. If you change R naught outside the loop, it won't necessarily change the value of beta. Let's try this. So here we have R naught equals 4. Normally I would say m dot R naught equals 10, for example, and see if that changes things. If it does, we're okay. If it doesn't, we're going to have to do things by hand. It does. And the reason for this, again, in antimony, is that antimony is parsed once when you do this load function. And these arithmetic relationships, like the one for beta, are not reevaluated if you overwrite. So if I change the value of R naught, it doesn't change the value of beta. So what I would have to do if I want to change my value of R naught is I would have to change beta. I'd have to say m dot beta equals m dot R naught times m dot mu divided by m dot S naught. And if I run that now, I'll get the new value. So why don't people, now that you've got that to look at, I'd like everybody to take just a minute or two to try on your own to write a little routine that will plot, change the value of R naught and plot max I versus R naught. Is that clear? What I'm trying to ask people to do. So I would say, so again, I'll just type it in the chat so as a reminder. So write a small routine that sweeps R naught. And we know that making R naught small, too big, too small doesn't do much. Let's make R naught go from 0.1 up to, we can make it go up to 15 in steps of 0.1 and calculate max I and assemble in an array and plot. Okay. So why doesn't everybody just take a few minutes to try to do that? And we'll see how that goes. And you're free to look at your old homeworks or your old problems and make sure that that works. And Julie, I don't know if you want to type up that code, your version of that code so that you got it to put in the chat, that would be fine.
Sure.
There are many ways you could do that. I tend to use VStack and HStack. I know a lot of people don't like those. So if you have a better way to do it, share it with your classmates. And we could also, maybe it's worth also printing that final number, percentage infected at the end. Actually, well, there are a couple of numbers one could plot. One of the numbers that might be interesting is the fraction recovered versus susceptible at the end. But we could also just plot the final number infected as well. And so the final number infected would just be I. So we could also print m.I, which is the final number infected divided by m.S0. And we can see how that varies as well. The final number infected isn't that interesting. Although 2% of the population infected all the time is not negligible. And I'll start a poll again, just when you're done with that little parameter scan, you can click finish with exercise. If you need, take your time. I'm not trying to rush you on it. If you're done quickly with that exercise, you could begin to do something which is a little bit harder, which would be to try to calculate the period or the duration of the waves. And so to do that, you would look at the time series either for R or I, find the maxima of that, find the time interval between the maxima, and get an estimate of that. And so I'm not going to ask everybody to do that in class because that takes a little bit more work. But if you've got the base exercise done and you don't want to be bored, please try that. And you could share that code with your classmates when you've got it. That was one of the homework problems, was to do that analysis. And, in the homework that I got back from people, nobody did it. So somebody may have handed it in since the problems that I saw, but not everybody, nobody did it when I asked for it. And so I'd like to make sure that we can all do it together. Again, there, and Giuliano, if you feel like trying your hand at that, there are a number of ways you can do it. But it does take a little bit more work. Right. So if you've done this base problem, Benjamin, if you want, try to think about that. Write a little code. You can look at that column for R, for example. You can look at the values. I think there actually is a NumPy function that'll actually find the maxes for you. But to begin with, you can walk through the values, look for the values that are maximal. So a maximal value will be bigger than the next value. It'll go up, the values will go up, down. So you look for the peaks, record the times, and then come back and do the analysis. So that looks reasonable, Brian. The one thing I might not do is I might leave out that in your chat. I might leave out that exponentiation because we don't, huge values of R naught are not reasonable. The actual experimental values of R naught are between 1 and about 20. I don't think there are any diseases for which R naught's much bigger than 20, maybe 30. But that looks fine. Let me do the poll one more time and see how people are doing. And you can definitely try out Ryan's suggestion. We can try it out together. So, yeah, you set up an empty matrix. Did I load NumPy? If I didn't do that, I better do it. Import NumPy. I'm so used to having it there, I forgot. So we'll do NumPy empty. There are a couple of ways you can specify an empty array, but shape is fine. Equals 0,2, perfectly reasonable. And then we'll do 4, let's just do 4 R naught in NPy dot arange. And we'll start with 0.5. We'll go up to 10, say, in steps of 0.1. And we'll now set R naught to be our new value of R naught. And we better, if we're going to do this, we need to reset our parameter values. So we need to do and m dot reset all on the function. And we'll run our simulation, calculate our maxima, and we can then put that into an array. And Ryan suggests using a VStack, so we'll do that. VStack of matrix, comma, R not, comma, X, I, and let us, let's actually, I'm going to do both the max I and the final value. It may not be very informative. Maybe they need to be together. So m dot I, these need to be normalized. And then we need to do our plot. Does that look right to people? Let's see. So, well, shouldn't have printed all that stuff, probably. And my plot is empty. Why is that? Turn this one off, turn this one off. R not. Max. Okay. Not that one. Nothing. Juliana, what did I do wrong? R naught, max I over m dot s naught, m dot I over s naught. Huh. The values are not going up. R naught is not what I think it is it?
Should be.
That's the value. Empty.
Empty.
So why is it empty?
I'm not familiar with VStack that much. Do you have to do matrix equals VStack?
Oh, that's, thank you. I cut and pasted from Ryan's code, but lines, but I from taking it out of the comment, I lost it. There we go. There we go. So did people able to get that? That's a nice way to do it too. The other suggestion here, Benjamin had a nice way to do it as well, using a pen to get the maximum. Were people able to get something like this? Let me just make sure everybody got this. So what you see here, if the x-axis, I can put the x-axis is, except it's not x title, right? It's x label. It's inconsistent between plot array and plot. I'm pretty sure it's, I think it's x label. No, maybe it is x title.
No, the issue there is because you You have
The order.
matrix after X label. Python is weird about the order of things.
Label, so this would be I naught. There we go. And that would be the fraction infected. So you can see that the maximum infected at any given time goes up as R naught goes up. For R equals 4, it's about 40% of the population. For R equals 10, it's about 70% of the population. Clearly, that's not what happened. Even with Delta variant, we're not getting 70% of the people infected at once. So that's not a very good estimate. But it does give you a sense that going from 4 to 10 doubles the number of infected people at any given time. If I only show the it's a little hard to see the final number of infected individuals. Let me do that. Separately. And here I'm going to take out that max I and just look at the final value. We have to make this by 2. So it'll be easier to see. Notice these oscillations. That means I didn't simulate long enough. The percentage, the maximum percentage goes up from 0 to about 0.2. If I actually want the simulation to terminate, I have to simulate for longer. There we go. So the final endemic rate of infection goes from 0 up to about 0.2 for large values of R naught. Does everybody get something similar to that? And now we have this nice. So Benjamin, this is your code to calculate the time interval between the maxima. Is that right? No. So that's max R1. Oh, so you ran the scans for all. So you were scanning for all the different parameters, but you weren't looking for the period. Okay. So people can try his code as well. Okay. That's great. Okay, so how many people are following this? Again, I know coding in front of you isn't necessarily the most exciting thing in the world, so I hope people are being able to do this together. But it's hard for me not to do it. I could ask you to do it and then call on you to do it, but I don't want to force people to do it. At least not too much. Okay. So this issue of calculating the period, Giuliano, do you have code to find the period?
Getting there.
Okay. So let's go on to the next problem. And maybe I should be saving this, but I'll save it after when we go back to the other. So now we're going to introduce vaccine. And so that was the last problem in the homework. And instead of clobbering what we have, I'm going to copy all of it and put it in a new version. And so now when we think about the vaccine, we have to think about an additional population. So what happens when we vaccinate people? And again, there's a problem because I have a typo in the arrow diagram here when I cut and pasted it. For vaccination, what we're going to do is we're going to assume that vaccinated individuals are less susceptible, but not completely insusceptible to the virus. We're going to assume that once they're infected, they're the same as people who were infected normally, which seems to be the case. And so what we have to do before we do anything else about the vaccination is we're going to create a new population, E4, which is going to be vaccinated individuals, and they can become infected. And they're going to be infected at a rate 1 minus, and epsilon is problematic. I think epsilon is reserved. So let's just call it 1 minus eps. Or why don't we call it efficacy for the vaccine efficacy? 1 minus efficacy. And then everything else is going to be the same. Beta times S times I there, like that. And so this means that if people are vaccinated, they can become infected, but the rate of infection is lower. So rate of infection of vaccinated individuals. Right? And let's assume to begin with that the vaccine efficacy for the alpha variant was about 95%. All right. And so now we're not going to, let's go back to our old situation where we're going to just run the base model. And plot it. We don't have to run it for that long. And plot it. And what we're going to do here is we have to decide what fraction of our population is vaccinated. And so let us start out with nobody vaccinated. We should get back what we had before. Let's assume that we have what we have today here in the United States, which is 60% of the population vaccinated. And that would mean that we have I is started out at 1%. Again, we'll set V, the vaccinated population, is 0.60 times S naught. And then the number of uninfected individuals is S naught minus I minus V. Because if they're vaccinated, they're not available to be infected. And to begin with, we're going to assume the vaccination lasts forever. Okay. And if we do that, we see that where's our vaccinated population? Our vaccinated population is 60%. It goes down gradually. The fraction infected maxes out at about 25% and gradually goes down. And it's telling me I'm not supposed to have a break, but it did what I want, which is not print all the other stuff. So that's not a bad approximation. And we can then ask the question, for example, why is recovered going up and vaccinated going down? Basically because we're not having any new vaccinations. We have this long decay. Now, that's assuming that the vaccination lasts forever. What do I have to do? Let me see if I got the correct next slide. Yeah, the next slide is correct. So let's compare just two things. Let's look at the initial epidemic again. Actually, probably have to make this time shorter here. 4,400. There's our initial epidemic here. And let's compare what happens in terms of the maximum number infected. The max number infected was max I, so we'll take that out, put it back up here. The max number infected was about 5% of our population for R naught equals 4. Now let's look at what happens if we go to the Delta variant. R naught is 10, and our vaccine efficacy goes down from 95% to 80%. What's going to happen to the max infected? We had 5% here. What happens when we run that? 22% of our population is now infected at one time. So we've gone from an epidemic where basically we were under control because of the vaccination to one where 22% of the population is infected at once. If we had 22% of the population infected at once, our hospital system would collapse. All right. So the last thing that we have to do to this is here I've assumed that the vaccine itself lasts forever, but you can become infected and then you go back to the recovered state. Let's assume that the vaccination doesn't last forever. And so our vaccinated people are going to go back to being S after some amount of time. And that time will be the same as the loss of immunity here in E3. So we're going to say that the vaccine, that actually is on the next slide here. S goes back to being, so the vaccinated goes back to being susceptible at a rate V over T. So let's do that, E5. The vaccinated people go back to being susceptible at a rate V over tau. This is loss of immunity for the vaccine. Let's see what that does. So what happens when we add that in? What happens when we add that in is that the fraction vaccinated goes down because we don't vaccinate any new people. They're all from the beginning. And the fraction of people who've gotten the disease goes to everybody. Effectively, everybody gets it eventually. At least in this case of high infectivity. My value of V is going negative, which means I've made a typo. So what did I do wrong? V goes to, somebody should have caught that. This should have been a V, not an S. There we go. That's better. So let's do this correctly now. Let's go back and do it correctly. I'm going to get rid of my loss of vaccine efficacy to begin with. I'm going to reset my value of R naught to be 4. I'm going to reset my efficacy to 95. And let's get the numbers right. There we go. So 5% of the population is maximally infected at once with the alpha strain. Maybe I should keep these values as a comment. Let's do it for the Delta strain. Alpha. And the vaccine efficacy, alpha. Copy that. Vaccine efficacy for Delta is 80. And now if we run that, 35% of the population are infected at once. So the last step of this homework was to now include revaccination. We're going to vaccinate people. And that would be a group that would take, before that, we're now going to say that we lose the vaccine efficacy. So I'll put this one back. And now without the vaccination, 36% of my population gets infected at once, and essentially everybody gets the disease for Delta. For Alpha, starting with 60% vaccination, eventually looks like everybody still gets the disease, but only 7% get it at once. And the last thing that I wanted to do was doing what we're doing in the reality, which is say, we're going to say that we're going to continue to vaccinate people. So we're going to take people from the category S to vaccinated. In principle, we could also be vaccinating Rs. So we could do that, although it's not going to change anything. And if we vaccinate people, we need to know the rate at which we're vaccinating. And here we'll call that new. And I know people got a little confused because new looks like a V. So I will call it new times S. This is the rate of vaccination. And in principle, we can also take our Rs and vaccinate them. We're not going to do that at the moment. And we actually know for the US that the vaccination rate is about 0.2% per day. So our vaccination rate new is equal to about 0.02, which is the vaccination rate per day. And let's see whether that makes any difference. Well, it slows things down. Did I make a typo? Giuliano, did I have a typo there? New is, okay, the rate of vaccination is new. Units or days. No, that's about right. This is for the Delta variant, the Alpha variant. And so we get 0.4%, starting with 60% vaccinated. And now let's go back to our Delta variant, see whether that does anything, keeps us under control. This was the last exercise, except for calculating the time. Vaccinating 0.2% per day, we still get 35%, 35% infected. Yes, that's a good point, Benjamin. Benjamin makes the excellent point that if you vaccinate the R population in this model, you make things worse because the vaccinated people can get sick and the recovered people can't. In reality, unfortunately, you can get sick after being recovered too. And so actually, you're right. You're actually taking the, that's exactly right. It's a strange assumption of the model. That's the case. Good point. Very good comment. And so, very perceptive comment. So let's just see what happens here. We get 35% infected. What fraction of the population do we have to vaccinate per day to get the Delta variant under the same control as the Alpha variant? Well, let's assume we could somehow vaccinate 20% of the population a day. If we could do that, we still get 25% of our population infected early, but it does pull the long time infection down. There's no way we're going to vaccinate 20% of our population per day. 2% of the population per day we could probably do. But the US is currently vaccinating 0.2% per day, which isn't anywhere near enough to keep Delta under control. All right. And Giuliano, you have put in a nice some code for this. Oh, there's actually a special function to find peaks in data sets.
Yep, and it works pretty well. You can define what plateau so that it only finds peaks above it. And yeah, it's powerful. I just used it without any options and it just did the job well enough.
Well, should that work with my code or?
It should, as long as you have the first line that I pasted. So it's from scipy.signal import find peaks.
So let's see, where would that go? Okay, but the well, I think I'll let people play with that on their own. I think it's probably enough coding in public for today. What do you think? We can upload that for them later. Unless are people very eager to see how to do to look at this function for finding the peaks? I'll let you vote on it. How about that? If people would like to have Giuliano show you how to do the peak finding, say finished with exercise, and if you don't want to see the peak finding, say need more time. How's that? All right. So Giuliano, you want to screen share and walk us through your code?
Yeah, sure. Just give me 1 second. Yep, if I can grab the share. Okay, here we go. This is no, that's the wrong page. Sorry. Okay, here we go. So, pretty similar to what you have. I've created a function that just changes the SRI model string so that I don't have to do the m dot r0 equals stuff. But everything else is pretty much the same. So I define my R naughts that I want to do. I have this matrix set up to get the results. And this for the periods. So I change the R naught in the string, load simulate. You had all of this, and then finding the peaks is just that. And to get this function, you only need this. From SciPy signal import find peaks. If I search for it, here's the manual page. Has options for thresholding where the peaks are, what's the change in the value needed to actually be classified as a peak. Guess this is the distance from one peak to the next, so that it doesn't find noisy data, it doesn't find things together. And it gets results like this. So this has a minimum of 0 to be a peak. This has a minimum and maximum, and it works pretty well.
If you use it, then what is the peak interval for our alpha and delta viruses?
Alpha and delta. Okay, what were the R naughts for them?
So R naught was for alpha, it's R naught is 4, and the vaccine efficacy is 95%.
Oh, I don't have vaccine yet here.
Okay. Okay, but that's okay. For alpha, so R naught is 4 for alpha, and R naught is 10 for delta.
Okay. Yeah, so for alpha, the periods were between the peaks were between 3,000 days, I guess, and 2,500 days. And
Something's wrong there.
Yeah,
the periods aren't. It's because it's the number of lines. It's not converting it to time.
True. Yes, that's right. Yeah, it's getting the
index.
Yeah, it's getting the index, and I'm not. Yeah, and I'm just passing the index instead of the time.
So you'd have to read the time value from that
and then
row.
pass it on. Yeah, it's an easy fix. I can do it afterwards. But in any case, we can see that it halved the period, give or take, which makes sense with doubling R naught. But to get, so to get the values of the peaks, it would be this. So the times would be this. And I think this should work. Let's see. Yes.
Yep.
Yeah. Yeah, so about 100 days for alpha, and then 50, 60 for gamma.
So that's actually sort of an interesting result, because with the switch over from alpha to delta, the duration of the waves doesn't seem to have changed.
Yep.
And so that leaves an interesting question, which is it because the initial population is different, so we have a higher natural immunity once delta started? So, or is it something else? Is it something that's fundamentally wrong about the model?
Mm-hmm.
It could be that R naught has changed, but the recovery time has changed, for example.
Mm-hmm.
So that's why looking at these parameter dependencies would be rather interesting. So figuring out the time interval is a function of the parameters. I'm not saying we're going to do that right now. But if you want to work on that, Giuliano, while I lecture,
yep,
we could try that. But that's great. And so if you can download and share that code with everybody,
mm-hmm.
maybe work on it a little bit more, but then share it. I think that would be really great for people. I hope that it was helpful at least a little bit to see how to do some of the solution for these homework problems. I don't want to take too much time coding in front of you, but I think it's also important that we do a little bit of that together to keep people on the same page. So what I'd like to do now is talk about stochasticity. And we're not going to investigate stochasticity in a huge amount of detail this class. Some people, when they were looking for possible problems to replicate for their projects, came across the idea of stochastic or Markovian models. So in our initial models, we've assumed, for example, that the rate of infection of new individuals here is proportional to the n number of encounters times gamma, the infectivity per encounter. And we've assumed that essentially every encounter is the same. But if we think about infection as a discrete event, you either are or are not infected. And so if you don't infect somebody, the person you didn't infect can't go on to infect others. And so in an agent-based modeling framework, you would actually model each individual, and you would model each encounter separately as a stochastic event. You would say, here's an infected individual. During the period they're infected, they encounter a certain number of people per day. On each encounter, you would roll the dice, so to speak. You would check whether you had an infectious event or not. And then those people who were infected would go on potentially to infect others. Some infected individuals would infect lots of people, some would infect few. The average number of infections would be beta, but that there could be variation. And potentially not only the average value, but also the variance of the infection would be important. And what you get would be what we're called chains of infections. I cough on somebody, they cough on someone else, they cough on someone else, they cough on someone else. And you get a chain of people who've infected each other. Eventually, of course, if the virus dies out, every one of those chains is broken. You end up with somebody who doesn't infect anybody else. And there are very nice ways of dealing with that. Antimony is not the best way to deal with that because you actually do have to model each individual separately to do that. However, there is built into antimony a stochastic solver, which does in fact run individual replicates in the probabilistic way that I've described. It won't give you the chains of infection that you'd get in a single agent-based model, but it will give you the fluctuations in infection that you would expect to see in reality. And one of the nice things about antimony is that if we want to use that, we only need to change one line in our simulation. Instead of saying m.simulate, we say m.Gillespie. One thing that you have to be aware of for Gillespie is that the basic Gillespie problem doesn't do fixed time steps the way the simulate does. And so when you output the simulations, you'll get pairs of time and number, and those times may not be equally spaced. You can look up in the Python, the antimony cheat sheet, how to use fixed time intervals in Gillespie, but traditionally Gillespie doesn't do that. It's the time to next event. And so what I'd like people to do is go back to the simple SIR model, which we had already. And with that simple SIR model, let's run the Gillespie algorithm and see what happens. And what I'd like you to do also is change the values of n, gamma, and mu to be 10, 0.1, and 1/5. So this is basically modeling something more like the Delta variant. And instead of using a large population of 10,000, start with an initial population of 100 and one individual infected. Okay? And I want you to run it 10 times and see what happens. Is that a clear? Oh, Giuliano, thank you. You said that decreasing mu by the factor that R naught is increased keeps the periods roughly constant in the simulation. So yeah, we could definitely, maybe Giuliano, you could work up a little bit an exercise that would illustrate that. So you maybe create a demo and we can have that for fun. But for the moment, I'd like people to try this Gillespie algorithm. Again, you're not going to have to make many changes here. I'll edit it while you do, but I want people to do this on your own, essentially, for the moment. I'm just going to type the version that I've got here. Okay. This doesn't happen in our world. Okay, so that's our old simulation, just so that I have it available for people. And let me just run the poll and see how people are doing. So is it clear what the question is? You want to take what I've written here or whatever you have in your own work, because you should be saving your models, your basic SIR model, you run it with simulate, and then you have to change exactly one line, which is instead of running s.simulate, m.simulate, you're going to run s equals m dot Gillespie over the same time interval. That's all you have to do. So let's do that again. See how it's going for people. And take your time, don't rush. And if you've already got the answer to this, I said run it 10 times. So if you've got it already done, and you're working and you want to go ahead a little bit, plot the 10 replicas on the same graph and see what it looks like. And maybe type into the chat what you saw. It would be nice if we could share images in the chat. I don't think we can. Okay. Maybe. No. I don't think so. So take your time, but I do want everybody to get through this because it's an important exercise. And if you have any questions or you need help, let me know, and we'll do our best to help. Thank you. So there was a comment from Benjamin that that he gets only straight lines. It's possible that the parameters are set wrong, or it's also possible, but you also have to do a reset if you're going to run the simulation multiple times. So let's see what happens here if we run it. If I run it. Yep, I sure get only straight lines. So why is that? Let's see. I've got I not equal to 1. That's right. N is equal to 10 here. Gamma 1 is 0.1. Correct. I is 10. That should be right. So I certainly in this simulation get some cases where there's no infection. Let's see if I run it multiple times. What happens? So I'm going to run this one 10 times now, and I'll do the plot. So let's see. So for n in range 0, 11, 1. We'll do a reset. And then we'll run Gillespie. And then we'll do our plot. And we'll do a show equals false on the plot. That may be a little hard to. Let's see, show equals false. And then we need to do the show and that show. See what happens. There we go. So what happens is that each time you run it, you get a different answer. Some of the times you run it, you get nothing happening. Sometimes you get a lot of people infected early. Sometimes you get a few people infected early, and then it takes a longer amount of time. So if you run it 10 times, do you get something comparable to what I got, or how does it look for people? I'll go around the room. Allie, what did you get?
I'm still working.
Okay. Okay. Ryan, how about you? All right. Delaney?
I'm still working too.
Okay, no worries. Take your time. Benjamin, did you still get zeros all the time, or did something happen?
Oh, I was rather than putting them in the loop, I was just copy pasting, and I forgot to put reset, so that was on me.
Well, I no guarantees. So just because I think it does something doesn't mean it does. Colin? Drew, do you have anything to results? Sorry, I better should put this back to let me get rid of the stuff we're not using. If people want to see this. Okay, thank you, Drew. So what's important here is that if I compare the deterministic result to the stochastic result, there's sometimes when even though overall the infection is strong enough that I should expect to see an epidemic, sometimes the infection doesn't take off, it dies out. And those horizontal lines people are seeing are when the infection dies out. And there's a huge range of times over which the infection operates, and a huge range of final number recovered is the total number infected. Notice something interesting though. I either have a situation which almost nobody gets infected, so the number of recovereds at the end is basically zero or very close to zero, or essentially everybody gets infected. I don't see cases in the middle. And so what that means is that the stochasticity is determined by what happens when there are few people infected. If enough people get infected, everybody gets infected, or almost everybody. But early on in the epidemic, if the epidemic dies out when only a few people are infected, then basically I never have an epidemic. And this is a bit of an explanation about why you see the spatial heterogeneity that you get in the real world. Even though the infectivity may be large, there are small populations, some small town, some group of people, some household, where stochastically the virus didn't spread and those people never get infected. And so that's actually rather interesting. If you're still working on this exercise, that's fine. If you want to go a little bit further, and you've already got that done, you could try changing the number of individuals. Suppose we started with 1,000 individuals instead of 100. If we change to 1,000, you'll notice there's still some fuzziness, but in general, it looks much more like my deterministic solution. What if I went down from 1,000 to 10? If I go from 1,000 to 10, I get all sorts of situations where the virus dies out after infecting one individual, two individuals, three individuals, four individuals, and so on. So the smaller my population, the more those fluctuations matter. And so I encourage you, while we're waiting for people to catch up, to play with these parameters. If I change to go back to that initial number of 100, you'll notice even with 100 individuals, sometimes there's non-infection. Start with 100 individuals, and now I could say, what if the initial fraction of population infected was 10%? Then it's pretty smooth. If my initial fraction infected was 0.1%, even with 100, there are many cases where there's no epidemic. In this case, this orange one here at the end in this simulation, it looked like the epidemic had died out. It went on for 30 days with no infections, and then suddenly it came up, and then the infections died down again. You'll notice in this case, I also get some intermediate values where the infection spreads a bit, infects a significant number of people, and then stops. And so what this is telling you is that you really have to worry about whether these continuum models, these ODE models that we're working with, are really representing what's happening in a real world population. If you have, and you can ask the question, how big does the population have to be for the fluctuations to not matter very much? And I think we can do that. If I start with 10,000 people, I get nice smooth curves. I get some fluctuations, I get some variation. But fundamentally, I don't have much difference between these curves and what I'd get with that ODE model that we started with. If my initial population is 100, in the case of 100, I probably have to make the fraction infected bigger. If my initial population is 100, I have qualitatively different results. I have failure to infect, and I have a lot more stochastic variation. If my initial population is 50, I get situations where half of the population gets infected and then the epidemic stops. So this would be breaking of the chain of transmission. And so the question of, is the simulation approach that we have used, this continuous approach, reasonable, is going to depend a lot on the size of the population and the initial fraction infected. It's also going to depend to some extent on your R0 value. If I make my R0 value, I didn't print my R0, so I could probably do that. And remind myself it's 5 here. What if I change my R0? Well, I can change my R0 by making gamma twice as big. That'll make my R0 10. If I make gamma bigger, it actually doesn't change the results very much in terms of the probability of dying out. And so I'd like people to play with that a little bit. Again, I want to make sure that everybody's able to get that base simulation working. And so I'll wait for everybody to do that, because that's important. But if you have gotten that working, I encourage you to try doing these extra simulations and explore these results. And certainly in the homework problems, when I say things like explain what you see, or I say explore the results or try out what happens, these are the kinds of things that I'm looking for. And that's part of the reason I'm doing this with you today. I want to try to give you an idea of how to ask questions about the models that you're working with. And if I ask the question, is the model reasonable? This would be a good example of a question, a case where you have to ask yourself seriously, is the model reasonable or not? Both the continuous SIR model that we started with and the Gillespie one. In reality, these kinds of fluctuations are probably more common than the very smooth, predictable things that we've been working with so far. Are there any questions about that that I can answer at the moment while we're thinking about that? The Gillespie solver to me is one of the big advantages of antimony. It has its limitations, but the ability to compare by changing one line of code, the stochastic and the ODE, is really valuable. If you do things in MATLAB or other modeling methodologies, it's much harder to do that. So we'll wait until everybody's caught up. And if you need help getting it to work, just say, speak up. Giuliano's here to help. I'm here to help. One thing you'll find with Gillespie is that for the ODEs, only ratios matter. What matters is if you have 10% of the population infected or 20% of the population infected. For Gillespie, the absolute numbers matter. Multiplying everything by 10 changes the results. Because each individual really is represented as an individual. So n of 10 represents doing the simulation with 10 individuals. Clearly, the probability of having the disease die out is higher when you have 10 people than 1,000 people for the same percentage of infection. So I did the simulation for some different values of R naught and some different values of total population. And in this case, I used a slightly smaller value of R naught. I used a value of 2.5 instead of 10. So let's do that. I can divide gamma by 4 to get that. And when I do that, I see that the smaller R naught is, the bigger the fluctuation. And the smaller the population, the bigger the fluctuations. In these simulations, if I started with 10 individuals, I got a lot of cases where nobody got infected or a few people got infected and the epidemic stopped. With 100, I got a variety of outcomes, although in general, the infection propagated in the population. Even for 1,000 or 10,000, I had some situations where that initially infected individual didn't infect anybody else. And so the infection died out. If I started out with a higher initial number of infected individuals, like 100, then I always got the infection for 10,000 people. And so two things are important in this kind of situation, one of which is the total population. The smaller the total population, the more likely you are to have fluctuations. But also that initial number infected, because that small number of initial individuals means the probability of dying out is fairly big. And so we can explore that. And you'll have a little bit of a homework problem doing some of that exploration. So why don't we look at the dependence of the stochasticity now on that basic reproductive rate? We did that a little bit already. I changed the reproductive rate from 10 to 5 to 2.5, and I saw that the stochasticity is bigger. Why don't people spend just a minute or two changing the value of R naught? The best way to do that probably is to change your value of gamma for a constant value of population, for constant initial exposure fraction, and ask the question, how does the stochasticity depend on R naught? And you can either answer the question in person, unmute and talk, or you could type into the chat. The basic question is, if you make R naught bigger, are the fluctuations bigger or smaller? And is there something else going on besides just the size of the fluctuations? Yeah, I think Drew, that's right. Essentially the probability, if the R naught is, suppose the average number of people that you infect is 100. If the average number of people you infect is 100, then the fluctuations mean you infect 99 people or 110 people, but the probability you infect 0 people is very low. And so that means the probability of the infection dying out is very low. So if R naught is big, the probability of the chain of infection dying out is very small. On the other hand, in the continuum case, if R naught is 1.1, you still get exponential growth of the infection. But if R naught is 1.1, the probability I infect less than one person, 0 people, is pretty high. And so that means that the probability that my chain of infection dies out is pretty high. And so this is another reason when you have stochastic situation like real infection, that something like mask wearing is important. Because if the probability that I infect, if the average number of people that an infected person infects is 4, then most of the time the infection will continue. If you could get that infection number down to something like 1.5, a substantial number of people won't infect anybody. And that means that even if the R naught is bigger than 1, there's still a reasonable chance that the infection will die out. Okay, so for the people who are needing more time, is there anything we can do to help out that can help you get through this exercise? I'm going to go around the room then and ask people what they got. Ryan, what did you find?
Uh, I guess with a bigger value of R naught, the fluctuations are higher. Like it's like basically the stochasticity increases.
Okay. Benjamin, you found the opposite, right? You saw the bigger R naught get less stochastic. Was that right? Or what did you get?
Yeah.
Yeah. Yeah.
Well,
I'm sorry.
you can go.
Yeah. So that's why I was not replying. Like I basically like thought that it's the opposite of what he was saying.
Okay, I mean, I can be wrong, so I'm not saying I'm not sure I'm right. Okay, Drew, are you still having
Oh,
go ahead.
I was just going to say I was controlling the R naught through N. Maybe it's possible that if you were changing gamma or mu to change the R naught, that through changing those, you would get different results.
Absolutely. If you change R naught by changing mu, you will get different results from changing R naught by changing N and gamma. So that actually is absolutely right, because they're independent processes. The infection process and the recovery process are independent. N and gamma should behave equivalently because they only enter in the product. So Delaney and Ali, I guess, can we help you? Is there something you're stuck with that we can help you with? Because I want to make sure that you're able to do this. Is there something that is, if you want to screen share, we can screen share and debug. Or if you want a breakout room and have Giuliano help you in a breakout room, we can do that too. What can we do to make sure you both are able to get this exercise done? I'll create a breakout room. And Giuliano, maybe you can work and screen share with them one-on-one. Is that all right?
Yep.
Okay. I know it's difficult this is that in general, I think that using the Zoom is not a bad way to do this, I think, because it's actually easier for you to see it than it would be in the classroom. But the one time you really have more trouble is when somebody's stuck, because you can't go around the room and look over people's shoulders in the same way. So let's just look at what I got here for this. Here I was looking at R naught, and something interesting happened actually for R naught equals 1. For R naught equals 1, in the OD model, there's no epidemic. You don't get any growth of infection. But in fact, in this case, there were some cases where actually by chance, you actually got a significant number of people infected, even though you didn't expect it. And so for R naught equals 1, you actually get more infection than you would expect for the ODE. Similarly, for R naught equals 5, you would expect that for the ODE, almost everybody gets infected all the time. But we see these couple of cases, which are these horizontal blue lines, where, in fact, only a fraction of people are infected, or there's no infection. So there's actually quite an interesting simulation, and I assigned it, I'll try assigning it as homework this year. I did assign it last year. You say, there's a question, are we just plugging in different numbers for n, gamma, and R naught? To begin with, yes. Although I think Ali can't hear me if she's in the breakout room. That's another problem with the Zoom. Okay, so she's trying to. So one of the things that's rather interesting is you see these horizontal lines where the infection failed. And one of the things that you can calculate is what's the probability for any individual replica of the simulation that the infection dies out. And there's a nice calculation that was done by, there's a nice slide deck by Jamie Lloyd Smith at Penn State University, addressing these stochastic chain models. And they calculated the probability of the epidemic continuing or not as a function of R naught. This is also going to be a function of the number of individuals. It's not only a function of R naught. They started with one infected individual. And they calculated the probability of the epidemic dying out. And what they found was, Delaney, were you able to get the help you needed to get that to work? I know it's frustrating if the internet's not working for you. I know that can be a pain. So they start with one infected individual, which we didn't do here. We started here with actually half an infected individual. So we can make it one infected individual. And they asked the question, what fraction of the time did the epidemic die out? And in this case, as you might expect, for R naught less than 1, the epidemic always dies out, which it does for the OD case too. But even for R naught a little bit bigger than 1, the epidemic dies out. And then as R naught goes up, the fraction of cases where you have no infection, where the epidemic dies out, goes down. But even for R naught equal 5, 20% of the time, the epidemic is still dying out. And again, that's not anything that you could get doing the deterministic model. The deterministic model won't tell you any of that. So it's quite a different set of results. The basic outline for large populations and large R naughts for the OD models that we've been doing and will continue to do is fine. But a lot of the details about what the variation in outcomes are different when you do the stochastic models. Again, it depends a lot on the population size. It depends a lot on R naught. It depends on the initial number infected. If you start out with 10 people and half the population is infected, which we could do, we could say, let's start out with, let's just say S naught equals 10, 50, but let's start out with half the population infected. When I do that, my results are pretty smooth. When I start out with 5% of the population infected, I get a whole variety of results. Sometimes I have failure to infect, sometimes everybody gets it, sometimes some intermediate number get it. So basically in these stochastic simulations, you're controlled by whatever subpopulation has the smallest number of individuals, whether that's the number of infected individuals at the beginning, the number of uninfected individuals at the end, the maximum number infected in the middle, the probability of being infected in the middle. These are all, these control the stochasticity. And so in the homework, I'm going to ask you to write a simulation that calculates for each value of R naught and for the other parameters, what the fraction of times when you run it, you'll ask the question, did the epidemic proceed or did it die out? And then you'll try to see how that depends on R naught and on the total population, S naught. And here again, we're always starting with one infected individual, which maximizes the stochasticity. This result is a little bit tricky because you're going to have to decide what your threshold for failure to infect does. I'm sorry about the communication problems. I know how frustrating that is. So at least we'll have the slide deck for you and the recording, so you'll have that as backup. So you'll have to decide what your threshold for determining whether the infection died out or not is, and that's a little bit tricky. So the curve you get will be noisy, but it's worth doing this exercise because it really does tell you something about when you can make the continuum approximation and when you can't. So one of the things that I guess we're almost out of time, so I'll just introduce the second topic that I was planning on going over this time. Again, this course is not a prerequisite for anything. So if we take an extra week to examine something of interest to us, it's all right. We don't have to get through a particular amount of material in the class. But I do want to talk a little bit about, well, I guess before I go on, are there any questions about this idea of stochastic modeling? It's something that we're going to play with a little bit, but not as much as it deserves, probably. At the molecular level, when you ask questions about molecular circuits, fluctuations are very large. Many important signaling molecules exist in 5 copies, 10 copies within a cell. And so the probabilities that don't behave the way continuous reaction kinetics would predict. And one of the things that's pretty remarkable about our bodies is that despite that incredible fluctuation amplitude at the molecular scale, they still work reasonably reliably. They don't work perfectly reliably. That's one of the reasons you get things like cancer. But they work pretty reliably. And a lot of the molecular circuits that are used inside your body have the form that they do because they're relatively resistant to this kind of statistical fluctuation. And so the Gillespie method was originally developed to model molecular reactions, not to do the kind of infectious dynamics that we're talking about. But in fact, if you have person A and person B is infectious and they encounter and you ask, did they infect or not? That's very much like asking if you have molecule A and molecule B and they encounter, did they react or not? And so it winds up that the Gillespie algorithm to do infection, it works quite well to simulate infection. So one of the things that we can talk about, we've sort of jumped ahead with the first example we did, where we did SIRS models, where we had immunity fade after some period of time, and then introduced vaccination. And the thing that was most important about the SIRS model compared to the SIR model was that we saw those oscillations. We saw those decaying oscillations, the waves of infection. There are other classes of model too, corresponding to other kinds of viruses or bacterial infection. There certainly are diseases that provide no immunity, which would be SIS. You're uninfected, you become infected, and the moment you're over the disease, you can get it again. Many kinds of cold effectively give you no immunity. Fortunately, typically not the more serious ones. I'm trying to think of other infectious diseases that give you no immunity. There's certainly we're not talking about diseases where you have lifetime infection like HIV, but rather a disease that doesn't give you any effective immunity. And colds do that. I'm pretty sure gonorrhea doesn't give any long-lasting immunity. I think syphilis also doesn't give any immunity. So a lot of the sexually transmitted diseases seem to fall in that category. But it would be interesting for people to think about other diseases that give no immunity. There are other diseases, of course, that give you essentially lifetime immunity. Mumps is a classic example of that. But it's worth thinking about that. If we have an SIS model where we go from infected, uninfected to infected and back, then what we get, unlike the basic SI model or SIR model, is that we get coexistence. So we're going to wind up with a steady state where we get a fraction of the population that's always infected and a fraction that isn't. And that fraction actually can be fairly big. And so if beta is the infectivity of the virus and mu is the duration of infection, duration of infection, yes, then we'll get that the fraction infected at any given time is 1 minus mu over beta. And so again, if R naught is less than 1, you have nobody infected, as usual. But 1 minus mu over beta is going to give us effectively 1 minus 1 over R naught is our fraction infected. And so we can see what that does. And I guess, okay, the last thing I was going to do today was do antimony events, but I don't want to start a new project. Let me just tell you in a few words before we break a little bit about events. So as I've mentioned, antimony is not a programming language. It's what's called a declarative language. It specifies certain kinds of relationships, but the actual programming and execution is done by that load A and the simulate function. But antimony does have some programming-like features. One of them is that you can have events. So an event is like an if statement. An event is like an if statement. And you can name it just the way you can name a reaction rate. And the syntax is event name at parenthesis logical expression colon, and then what you want to have happen. And so one of the common things you'll do is at a certain time in the simulation, you want to make some change. At some time, you add infected individuals. At some time, you vaccinate people. You could certainly do that in the Python by running the simulation up to some time, using the Python to overwrite parameter values or variable values. But you can also do that within the antimony code. And so next time, we'll start out by talking about antimony events and how to use them. and how to build slightly more sophisticated models using that. So I'm sorry if anybody had any frustrations with the coding so far. I hope Giuliano was able to help you, Ali and Delaney, a little bit. Are there any questions now before we break for tonight? I didn't do up the homework tonight. I'll get it out for you tomorrow because I wanted to see how far we got before I set the homework assignment. Any questions or comments before we break? No? Okay. Sorry, go ahead. Sorry.
In
Nice.
homework 5,
Yes.
the so it references creating models from the the COVID data. Is that still just the data from Joshua's simulation?
So, yes, I think you probably, let's see. I have to think, I can't remember the homework problem. So what was the homework problem? I'd have to open up the homework and check on the exact problem that was set. So let me look for that. Sorry. So this was homework 5. And which problem are you asking about?
Problem 3.
Problem 3. Yes, so fitting to data. So the models we're using are SIR models. And the SIR models will not fit. They by definition, the SIR model will only give you one peak. You'll get a bump and then it goes away. The epidemic will go away. And so if you have multiple waves, the SIR model won't work. And so the assumption was that you would look at the first wave of infection in those countries. If you want to be ambitious, you could pull one of the other waves. So you could, in a country like Italy that had a major infection peak and then the disease went away almost entirely and then Delta came out and you had another peak, it would be interesting to fit Vietnam, where you didn't have the first peak at all, basically, and then you have a Delta outbreak. It would be interesting to fit that Delta wave as well and compare the results. But if you see a time series that goes up, down, and then up again, you won't be able to get that to work with just an SIR model. With the SIRS models that we've been playing with, you could possibly fit it. But you'd have to then pull the data set out and pick the time window that you wanted. Does that help?
Yes.
Okay, great. Good point. Anything else any other questions? That's a good point. I was assuming we would use that first wave data set, but in fact, there's no reason you can't use the later times, but you have to select a window with a single infection. Anybody else? That's a great question. Anybody else have any questions, comments? Okay, thank you, everybody. Giuliano, could you stay on for just 1 minute?
Yep.
Okay, I'll see you next week if I don't talk to you before that. If people are working on their projects and would like to meet and discuss project plans and ideas, that would be great. I'd like to try to do a paper replication exercise. Depending on, let me think about whether we want to do that next week or the week after. Because I want to get through the antimony events but that doesn't take that much time. So maybe we can do a paper replication next week. If we decide to do that, we'll send it around and have everybody look at those. A few people sent some ideas for papers to replicate. I really would like it if everybody would contribute one paper as a possible project, mini project for in class, because those paper replication in the past semesters, that's been very productive. Okay, well, thank you, everybody. Good night. Get some rest, get something to eat, and I will look forward to talking to you again soon.